Yeah, I just wanted to say thank you so much for joining the opportunity to present. Yeah, I know you've joined into the Geo-AI working group in the past few months, and you've been really vocal and really sort of engaged in the working group already. It was fantastic to see. I know you're going to be contributing to the book as well. I think there's a lot of people within the SERVIR office, like right in down this hall, who are joining us, do a lot of work on ag as well, and are really interested in your research. And I think this is a really great opportunity to just hear more about what you're up to and the efforts of your PhD. So I will stop talking and I'll hand it over to you.
Yeah, thank you so much, Tim. Good, great. Thank you so much. I'm Chishan Zhang. I'm just a PhD student at the University of Illinois Urbana-Champaign. Today, I'm gonna introduce one of my recent work, which is using like a Bayesian deep learning models for the crop yield estimation and uncertainty analysis. But I think there are main two innovations of my work. So one is like we integrate some physical-based mechanism, which is here is a phenology mechanism into the deep learning model to help us to understand the crop yield process. Because usually they would say like deep learning models is like a black box. They are very hard to understand the process. And the second part is like we utilize the Bayesian theory to quantify the uncertainty during the crop yield estimation based on the deep learning models. And I will first introduce some background information here. So in fact, there are two mainstream crop yield estimation methods. So one is the process-based crop model. So this one usually will incorporate many complicated crop growth process and the soil process. So they usually be quite like accurate, but they need a very extensive like field level input data to calibrate the models, because there are many parameters, they are kind of regional specific. So you need to calibrate those parameters when you try to apply your model to a new region. So that really requires a lot of work and have a very like a kind of limitation for the data itself. So compared to this complicated process-based model, there are another approach which is directly using empirical models. So these categories just directly try to incorporate many different source of information like the satellite data or climate data, and directly build an empirical relationship between the satellite data and the crop yield. So those data usually are quite accessible, and so they are, especially at a large area, so they have been used a lot when you try to build a model to apply at a very large area. And within these categories, deep learning model definitely has been outperformed as others. And for now, there are many different deep learning models that has been applied for crop yield estimation, like ANN, LSTM, and CNN. And they share like very similar input variables. Usually they will use like remote sensing data, climate data, and soil data. But even though those models are very successful, they still face some challenges. So first one, I think it comes from the model structures. I already said, like there are many different informations like soils, climate, and like satellite data. So they usually have very different mechanisms. Like the satellite data, they just use the reflectance to reflect the crop greenness. But for the climate data, they usually just like a precipitation and temperature. They will like affect the crop growth. So they usually represent very different mechanisms about the crop yield. And they have different resolutions and data qualities and many different things. So usually it's very hard to use one model structure to process all those data, especially if you want to just build a very efficient and a small model. And second challenges come from the fixed time scales, or I would say it's like the phenology dynamic of the crop yield of the crops. because usually we know like phenology of the crops will affect the crop yield a lot, like and they can be very heterogeneous. Like if you look at the right figure, um, let me see. So if you look at the right figures, like at the same DOY, like 150, for there are 3 time series for different pixels. So you can see that for the orange ones, they already like approach the middle green up for this pixel, but for other pixels like the crops are still under the soil and they haven't emerged. So that's quite different. But for the climate data and the satellite data, they usually have a fixed time scales, like 8 days, 16 days, or monthly data. So the same time step for different pixels usually represent totally different meaning. So that causes a problem. So when you feed those time series into the different models, so each time step represents different meanings. So that causes a lot of trouble for the deep learning models to learn those patterns. That's from the model structure. And another challenge comes from the model uncertainties, because we know usually like if you want to predict the crop yields, you want to make some decision based on those predictions. But usually, like for different models, they are very different. They are difficult to have the model uncertainties. And if you don't know the uncertainties, they will have very high risk to make the wrong decision. And there are usually 2 types of uncertainties. One is what we call anatomic uncertainty. This one is a variation of the data or observation. And another one comes from the model, which we call epistemic uncertainty. This uncertainty is about the model parameters, and usually is due to the limited training data. So if you look at the right figures, so I would say like the left part, they have those training data set, they have a higher variations. So we would say this anatomic uncertainty is quite high compared to the right part, because the right part, they are just the variation is much smaller. So when you train the data at this part, usually the anatomic uncertainty is smaller. And for the middle part, you can say there's no any training data. So that causes a problem. Like if you do not have any training data here, and if you want to predict the crop yield at this range, the uncertainty will be also very high. So what we want to do is just to try to distinguish those uncertainties and quantify them. So here, just to address those issues, here we just developed what we call the PBCN framework for the crop yield estimation. So here we just use soybean as a study case. And we have 3 objectives here. So first, we want to incorporate the phenology dynamic into this framework. Like we said, the phenology can affect the crop yield a lot, and they are very heterogeneous. So if we can incorporate those dynamic into the framework, it can help us improve the model accuracy. And the second, we want to develop a multi-stream Bayesian-CNN model, which can help us to process the multi-source information and do the uncertainty quantification. The third one is we want to also analyze the feature importance and the 2 different uncertainties. So my study area, we choose the Corn Belt, which is like the main soybean production areas in US. This is a very high production area. Usually it will cover about 40% of global soybean production. So this is a very important place to study the soybeans. And you can see that we use many different data to predict the crop yield. And we use the satellite data, phenology data, and heat stress related parameters and water stress related input variables and the soil variables. And my PBCN framework includes 3 parts. The first one is a phenology imagery construction. Because in this study, we try to predict the crop yield on the county level. So we need to aggregate the original time series data into the county level. Like if you look at the left figure, so our original input can be like the modest time series. But like we said, each time step for the time series could have totally different meaning for different region. So here we just use the phenology stages, like to divide the whole growing season to 6 different stage. And because we use the phenology information for each pixel, or you can say for each locations, so they would have the same physical meaning. And after we divided the whole growing season, we will aggregate their information into each stage, like using the mean values, maximum values, and the minimal values to represent the information of that stage. So after that, the whole time series will be aggregated to only like 6 images for each county. And after that, each county is still an image, but we know like each counties have irregular shapes and different size, so it's very hard to be processed by the CNN model or other deep learning models. So we still need to do the spatial aggregation. So in conventional ways, usually we will use like the mean values, like the average the pixels across within the county. But we know like each county is not a small areas, and usually the information within each county can be heterogeneous. So here we do not use the mean value, we use the histogram. So we transformed each images into one histogram, like the left figure shows. So because we have 6 images, so we will have 6 histograms. So in fact, you can think about each histogram as one vector. So along the time step dimension, we can directly stack those vectors together to get imageries at the right side. What we call is like a phenology imageries. So for these imageries, so there are 2 dimensions. One is the histogram dimension. Another is for the growth stages. And you can see that there are clearly some patterns can be learned by people or by the deep learning models. So we will use these phenology imageries as the input for our deep learning models. And like I said, because these imageries already incorporate the phenology information, so this can help us to handle the phenology dynamic across different regions. So that's for the first part. The second part is about our Bayesian-CNN model structures. So you can see here we have multi-string structures because, like I said, we have many different input variables. They should have different mechanisms. So we just choose like separate structures to handle each input variable groups. And finally, we will combine them together to make them more efficiently to process different features. So the second part is like the Bayesian distribution part, because in the conventional CNN model, it's very hard to use them to predict the model uncertainty. But here, we use the Bayesian-CNN. So the main difference between the Bayesian-CNN and the conventional CNN are just their weight. Because in the left figure is just for the conventional CNN. The weights in CNN, they are just some point estimation. They are just numbers. So you can say that our input are numbers and the filters, the weights are numbers. So after the convolution, the output can still be a number. But the right side is our Bayesian-CNN model. So in Bayesian-CNN model, those weights become the probability distributions. And you can see that even though our input are still numbers, but because our weights are the as a distribution. So our output can also be a distribution. So after the convolution, we can have a distributions rather than a number. So in that way, we can quantify the model uncertainties. So the last part would be the feature and uncertainty analysis. Here we will just use a leave one out method to quantify the feature importance. What's special here is that because we have so many different features, we will not directly quantify their feature importance by each feature. In fact, we will group those features together. Like if they are related to the temperature, the heat stress, we will group them as a heat stress. If they are related to the water, it will be grouped to water stress and the soil group. And we will just quantify the feature importance for each group rather than each feature. And we will also do the feature importance for each phenology stage. So it will tell us which phenology stages is more important and help us to understand this prediction process. And for the uncertainty part, because like we said, there are two different uncertainties. One is anatomic uncertainty. So this one we will use just adjust the loss function to help us to estimate those uncertainty. And we will also estimate epistemic uncertainty, which is more related to the model structures and model parameters. And here are some results. So first is about the feature importance. You can see that if you look at the right figures, so there are two dimensions. One is for the different feature groups. Another is for the growth stage. So S1 represents the stage 1 and S2 is the second stage. So you can see that like if we look at the different feature groups, the EFI2 definitely have higher importance, which makes sense because EFI2 can directly relate to the crop biomass, and which is a very strong link to the crop yield. And if we look at the horizontal axis, you can see that the S3, S4, and S5, those three stages, they are more important than other stage. This is those three stages usually are just related to the soybean blooming, to the dropping leaf stages. So those stages are very important for the crop yield formation. So which make a lot of sense to our domain knowledge. And talking about the predictive uncertainties, so the second row is just the uncertainties for our study areas. The left one is anatomic uncertainty, which is more related to the data. And the right one is the epistemic uncertainty, which is more related to the model structures. So the main conclusion is here is like you can say that the primary uncertainty, in fact, it comes from the anatomic uncertainty. Because the range for the anatomic uncertainty, in fact, is totally different. For the anatomic uncertainty, it's about 6 to 2, but for epistemic uncertainty, the range is under 1.2. So usually it's much smaller. In fact, they have similar pattern, but the range are totally different. So in fact, during this prediction on a process, the uncertainty comes from the data itself is much larger than the models. And another interesting finding here is that we found that the epistemic uncertainty sometimes show a better consistency with the estimation errors. So if you look at the central part for the Illinois state, so you can see that our observed yield is much higher than the, not much higher, it's higher than the estimated yield, which is because in 2018, this year, the soybean yield in this part have a much higher yield than the records. So you can see that because those high yield records are never appeared in our training process, so our model cannot predict it very well. But you can see that our epistemic uncertainty also give us a warning because it told us there are very high uncertainties. Those data are never showed in the training sample. You should be careful. And those uncertainties are never, those patterns are never showed in the anatomic uncertainty. So it will also give us like some about the significance of the epistemic uncertainty. And if we look at what factors cause these uncertainties, we found that in fact, if we incorporate the EVI tool, it definitely help us to decrease the uncertainty. But if we look at the soil, you can see that they have very high uncertainties, and the rows grow like S1 to S3. They also have very high uncertainty. So it give us, let me think about this, because if you incorporate the soil, it will definitely help you improve the model accuracy to some extent, but it will also give you some drawbacks, that is bring very high uncertainty into your model. So the next time when you apply your model into a new region, there is more high possibilities to make mistakes. So that's one thing we need to be careful about. So in a summarize, we incorporate the phenology information into the deep learning models, which can help us to understand the yield response across different growth stage. And we use the Bayesian theory into the same model, which can help us to differentiate between different sources of uncertainty. And we found that the primary source of uncertainty for the estimation crop yields, in fact, it arises from the data itself rather than the model. And the last thing we found that the information on soil conditions and early growth stages can enhance the model accuracy, but also introduce additional uncertainties. And I think that's pretty much all. So feel free to ask any questions. Thank you so much.
That was fantastic. Thank you so much. Let's just open it up to everyone for questions. Let's see here. Diego, over to you.
Hi, that was a great presentation. It was very interesting, the approach that you had. And that's something that it's very important, like to have a different approach from the temporal aggregation of satellite data when we are dealing with crops, because crops are not, they have their own timeline. So it's very important what you are doing. So I have a couple questions. The first one is about the soil, because usually, like soil have different layers.
Yes.
And each layer can be more or less important on different stages on the crop. So did you include several layers as input, or did you summarize the entire soil profile into a single layer? How did you do that?
Yeah, so thank you very much for this question. That's a very good question. In fact, because we know like soils have different layers, and for different crops, in fact, we do not know which layer is more important because they can be very crop specific. So here in our study, we just incorporate like several different layers as use them as different variables. So I will directly choose them like a soil pH for different depths. I will directly identify them as a different input variables and use them into our model. Does that answer your question?
Yes. Thank you so much. And my other question is about the output of your model is a probability distribution. So what loss function you used if your output was a probability distribution?
So the loss function we used here is just is this one. Can you say that is the NLL loss function? So in fact, in this one, like because we directly assume the output would be a Gaussian distribution, so we can use the mean value and the sigma to represent the whole distributions. And
okay, yeah. I can see now. Okay. Thank you so much. Great work.
Thank you.
Hi, I have a question.
Sure.
Yes, so it was a great presentation, Sam. I have one question about the spatial ensembling you did after with the time series data. So what was the resolution for like when you are spatially combining those data?
So can you explain a little bit about the question? Like
yes,
the
yes.
temporal resolution for the satellite data?
You are getting the temporal data from the satellite data, right?
Yes.
Now you are spreading your data throughout the county level, right?
Yes.
So, like, spatially, how much they are spreaded? Like one county, the sizes of the county is different, right?
Yes. Yes.
So the distance between did you take any like centroid of the county kind of approach, like how those excuse me spatially data was
Okay.
combined?
Yeah, got it. I think I will try to explain that part. So there are two resolutions. First is for the temporal resolution, because we are using the modest time series. So the original temporal resolution is just the daily. We use the daily reflectance data.
Yes.
So and because we only have 6 different time stage, so so after we do the temporal aggregation, it's just become 6 time stage. So it's like so each time stage maybe it's just 1 month, but it depends on like the crop growth. If some areas their growth is faster, so this range will be smaller. But if growth like slower, that just the range will larger. So that's for the temporal part. For the spatial part, like you said, like because each county have different size. So the original modest data here is just 500 meter.
Yes.
And we directly use a boundary for each county. So we will use the all pixels within that county, and we will also use some like land cover maps to mask the long soil bin pixels. So we use the pixels within that each county and do the aggregation. Does that answer your question?
Yes. Okay, thank you.
Thank you.
Thanks.
Other questions on the line? I've got a couple. So on, can you go to the side by side of your observed and estimation and then comparing your different loss functions? Yeah, this is a really nice figure. First off, I just want to give you a lot of kudos on this. I feel like you've incorporated all of the uncertainty, which is such a huge field in and of itself, right? This approach is really bringing all that information into the final products and allowing you to discern, which I think often, I'll say for myself, I'm more interested in the product and not necessarily the process to get to it. So I think this is a really great approach to incorporate that uncertainty and allow that to be a knowledgeable element to it as well, as you showed here in this example in like Central Illinois. I could imagine that this approach could be really valuable across many, many fields, right? So it's really, really exciting. I just wanted to give you kudos on that. And 2 questions based off of this figure that sort of started rocking around in my head of, first off, could you speak a little bit about the data that you're using for your final product? Like, I guess your training data. Is this the county level reports, or is this like the NAS crop level layer? What's the reported amount that what is that data, I guess, is the first question.
Yeah, so this is just county level results, because like our input data, like they are like 500 meter or several like kilometer resolution, but we all just directly aggregated them into a county level and do the training on the county level and report the accuracy on the county level, because our yield record is on the county level. I believe like our methods, if we have high resolution yield record, they can be applied to a file like smaller scales. But because our yield record is on the county level, for now I can only provide the yield county level results.
Yeah, so for this method to really take flight, you're going to need those county level records. And the other assumption is like the fields or the domains that you're looking at are at least bigger than the pixel, right? So
yes.
Working within smaller fields generally, or I guess domains, might be more challenging with this MODIS approach.
Yeah, I think so. It's like because like in US it's quite homogeneous.
Yeah,
so that's easier to do this kind of prediction. But in some developing countries, like there are mixed pixels, we definitely need more efforts do, I don't know, maybe do the unmixing process or a higher resolution input to help us to have a better results.
Yeah, and as you're mentioning that too, I was thinking also intercropping, also that dynamic of multiple crops in the same season or cultivars in the same fields, that phenological signal might be also really challenging too. Something to sort of keep in mind when you're moving outside of these sort of monoculture applications. But that's really, really cool. And then the final question I had about, so the comparison of the observed and estimated, and then these two loss functions, which really sort of tell the story, I think. Could you speak a little bit about what's going on over in Nebraska, in the far western portion of Nebraska? Why these four? Why we're seeing these darker reds as to the prediction, I guess, or observed in the loss function here?
Yeah, definitely. So this is also one thing I'm very interested. So I do not have very a specific explanation, but I have some assumptions. So first is because you can see that the notoric uncertainty at these those parts are very high. So which means their data, the relationship between the input data and the yield records are quite unstable. Mm-hmm. So I think that caused from first is because climate conditions, they are usually different from the other states and this part because it's already approaching to the Great Plains, so they have more irrigations and also have different climate conditions. So if we try to build the model, if we build a separate model, I would say maybe their uncertainty would be smaller. But because we just incorporate all areas together, so those parts definitely are different from other parts. And our model just tell me the uncertainty is higher than others. Their accuracy should not be equal to the other parts. I think maybe that's the conditions and the data qualities and the irrigations the main source of high uncertainty at that part.
Yeah, that's a fantastic explanation. I think that extrapolation and the different conditions, it's really, really interesting because this is really sort of looking at the bounds of what is important or what can be, what kind of information you can derive from this model and the qualities of the data to begin with. I think, I'm not plugging this idea, but I think taking what you've done right now and doing an application in Eastern Southern Africa or Kenya or something like that on cassava or some other main crop might be really, really interesting, because then you could sort of tease out what data that's driving this model is really high quality or low quality as well. Could be a really interesting approach, but not to give you more work or anything, just brain churning. So yeah, any other questions on that? I don't want to eat up all the time. Oh, go ahead, Biplav, or I think it was Biplav.
Yeah, thanks, Chishan. Really great presentation. And really great that you're showing all this visually, so it's easier to understand what's going on. So continuing on this discussion, like epistemic uncertainty, you see there's it's higher than the other uncertainty, and that's probably because there's a gap or limitations in understanding the model. So I was wondering, like, is there any specific sources of uncertainty, especially on the epistemic? Like, there might be some additional data or improved modeling techniques that can help. And like, how do you plan to improve this particular uncertainty that we can probably integrate more data approaches in it?
Okay. Yeah, that's worth one question I have thinking about for the last month. I think that's quite issue for now because we can only identify uncertainty at that part is high, but we do not have very good approach to address this issue. Like how can we reduce the uncertainty at that part? But I think the main conclusion we can get here is it seems like for now when you do the crop yield estimation, the primary uncertainties comes from the data itself. So it's like if you try different models, so their uncertainty difference would be small. So it seems like give me a feeling that if you try to use more advanced deep learning models, in fact, it will not improve your model model accuracy a lot. In fact, if you try to use like a higher quality data or incorporate more information, that can directly help reduce your model uncertainty. Like at the left corner row state, if we have higher quality data for that state, and if we have irrigation data or have more information, I think it could help us to reduce the model uncertainties. Or like I said, it seems like for soil, their data quality can be very bad. Mm-hmm. Or so if you directly remove your soil data, it may decrease the model accuracy a little bit, but also improve your model uncertainty. So it's like a trade-off when you build increase your input information, but with very high qualities, it may help you have a better accuracy in a new regions.
I see. Yeah, and I guess this also links back to what Tim was mentioning. Like, if we were to scale this up in other parts of the world where the data quality is not that great compared to the US, I wonder how how accurate or how good this modeling approach would be. But that's something for another time. Otherwise, thank you so much. This was very interesting. It's good to see that you've also done the feature importance and those kind of stuff that also helps to maybe pinpoint a little bit on the data side of things and getting the uncertainty there. So yeah, thank you so much.
Thank you so much.
Over to Diego.
I cannot hear you.
Now you can hear me. I was muted.
Yeah.
Yes. I want to say it again that it's a great work because when I look at your feature importance, it makes sense, and that's really important. I work with process-based models, and a lot of people when they do machine learning model for yield prediction, they only care about the output, but they don't care about the model making sense. And by looking at your feature importance, it definitely makes sense. I mean, like what phenological stages are more important than others, and that's something that usually people miss when they are using machine learning for yield prediction, and you are not doing that. So again, thank you for showing this amazing work. That's it.
Yeah, thank you, Diego. It's just like you already said, like Biplov and the teams mentioned, I'm also very interested about using this model into the other developing countries where they are data limited areas. So it's just I'm more so like doing some research about transfer learning, but I found like the difficult part is like the data, like the year reports, the new regions. Yeah, I think hope we can have more like I can hear more interesting works from you guys in the next few months. Thank you very much.
Well, wonderful. We only have a few minutes left. I'll pause if there's any more questions on the line. Do a healthy pause here. All right. I just want to again say thank you so much. A really fantastic presentation. I know we gave you 30 minutes, but I feel like we could talk for about 2 hours on this. I think this was really, really great. You're welcome back for any future presentations. I know you're doing a lot of other research on your PhD. So if you've got other ideas in the coming months, as you're cranking out new papers and things like that, you're always welcome. And I just want to say to everyone on the line, I think we'll be back in 2 weeks with folks from NASA Goddard. So really excited about their presentation. And let me see here. I think I got a hand up. Oh, over to Biplov. Yeah, go ahead.
Yeah, I just want to plug in again, Chishan, if you have any research that you are doing that might suit for the Ag ML session, please feel free to submit it.
Sure.
100% on that.
Yeah. Thank you so much.
Well, thanks, everyone. See you all in 2 weeks.
Thanks, everyone.